Hey there, welcome to Learn with Longman. Today we're getting into the nitty-gritty of reaction rates. We'll break down how scientists measure them, check out some reaction rate graphs, chat about collision theory, and explore two handy diagrams, Boltzmann distributions and energy profile diagrams. No need to overthink it, let's jump in. Reaction rate is simply how fast a reaction happens. Some reactions take it slow, like rusting. Iron does react with water and oxygen to form iron 3 oxide, but this doesn't happen before your eyes. It takes a long time. On the flip side, combustion reactions, such as those involved in the burst of a firework, are often lightning fast. Once those reactants are mixed and ignited, it's an explosive chemistry performance. An important thing to remember is that reaction rates can be altered by changing reaction conditions. This is something we will explore in an upcoming video. Quantifying reaction rate involves measuring observable changes during a reaction. For example, dissolving an aspirin tablet allows us to observe the formation of bubbles and the reduction in tablet size. These changes can be precisely measured by collecting bubble gas and measuring its volume, or monitoring the tablet's mass as it decreases over time. The resulting expressions, like 3.25 mils per second or 25 grams per minute, provide quantitative descriptions of a reaction rate. Reaction rates can be observed in graphs. In the graph below, the volume of hydrogen gas produced during an acid-metal reaction is plotted against time. The resulting graph displays a distinct shape, offering valuable insights into the kinetics of the reaction. The slope of the graphed line serves as an indicator of the reaction rate, with a steeper inclination signifying a more rapid rate. Notably, the initial stages have a very high reaction rate, progressively tapering off over time. This phenomenon correlates with the diminishing concentration of reactants, initially abundant, but gradually depleting as they undergo conversion into products. The conclusion of the reaction is marked by a plateau in the graph, indicating the cessation of further product formation. Here is an alternative graph, depicting the dehydration of sugar by concentrated sulfuric acid. We measure the mass of carbon produced over time. Initially slow, the reaction rate exponentially increases before gradually declining. This kinetic pattern is typical for an exothermic reaction with a high activation energy. As the reaction progresses, energy release enhances successful collisions between reactants, leading to faster rates. The decline at the end is due to the exhaustion of all reactants. Let's delve into collision theory. In chemistry, it's the concept explaining how and why chemical reactions happen. It states that, for a reaction to occur, reactants must collide with enough energy and in a specific orientation. This theory underscores the critical role of the activation energy as a barrier to reactions. This is the energy which is needed to break bonds between reactants so that the products can form. When collisions occur between slow-moving reactants, they simply bounce off each other. However, when collisions occur between high-energy, fast-moving reactants, then bang, a reaction ensues. It also highlights that reactants need to collide in just the right way to get the reaction to occur. So in this example, they need to collide so that each hydrogen atom collides with an oxygen atom, as shown here. If this is not achieved, then no reaction will take place. Correct orientation is likely when molecules are small and simply shaped, but becomes increasingly difficult as they get bigger and more complex. When discussing reaction rates, we will often encounter energy profile diagrams, which illustrate the journey of a chemical reaction, providing valuable insights into key features. Consider the exothermic reaction between magnesium and hydrochloric acid. The reactants start the process with a certain amount of potential energy. As the reaction progresses, bonds within the reactants are broken, requiring an initial input of energy. The energy associated with this phase is the activation energy. As the reaction unfolds, new bonds are formed to create the products, releasing a substantial amount of energy in the process. The overall enthalpy change is negative. This means that the energy is released during the reaction and hence it is exothermic. Let's compare this to the energy profile diagram of water electrolysis. The general shape of the graph is similar, but there are some noticeable differences. First of all, you can see that the reaction is endothermic. This is recognisable as the products have higher enthalpy than the reactants, corresponding to a positive enthalpy change. We should also note that this reaction has a much higher activation energy and can be used to infer that this reaction is non-spontaneous and thus requires the input of energy, in this case, electrical energy. Okay, let's look at some Boltzmann distributions. An essential graph with kinetic energy on the x-axis and the number of molecules on the y-axis. It describes how molecules in a sample at a given temperature have a range of kinetic energies. The peak indicates the most common kinetic energy among the molecules, while the ends represent those with high and low kinetic energies. Take hydrogen peroxide for example. Its decomposition to form water and oxygen requires a relatively high activation energy, making the reaction non-spontaneous. On our Boltzmann distribution, we place the activation energy to the right of the peak. When we raise the temperature, the distribution shifts rightward, with more molecules gaining higher kinetic energies. The peak also reduces as the molecules now cover a larger range of kinetic energies. Conversely, colder temperatures narrow the graph so that fewer molecules contain high energy. Notice how altering the sample temperature affects the proportion of particles with enough energy for the reaction. These graphs can give us crucial insights into how and why reactions occur, and we will be using them in our next video. We're about to explore some questions from my Teachers Pay Teachers resource on reaction rates. If you find them beneficial, consider using the link in the video description to purchase the full copy for yourself. I designed these resources to ensure you have the necessary tools to approach tests and exams with confidence. In this question, sketch a labelled energy profile diagram and Boltzmann distribution for the dynamic reaction between permanganate and glycerol. Apply your understanding from the video. Take 7 minutes and return for the solutions. Okay, check out the marking guide. Did you correctly label the axes on both graphs? Have you accurately plotted the curves? Ensure that you label the enthalpy change and activation energy where required. These factors are crucial for achieving full marks. I hope this has been helpful. Remember to like and subscribe, and I will see you soon for another Chem session.